This lesson is all about radicals, whether it's simplifying radicals or dealing with various operations like adding, subtracting, and multiplying, and how to deal with radicals that are in the denominator of a fraction. But before we can get into that, we have to look at some terminology. First thing, this symbol here, that is your radical sign or your root sign. The number in the little triangular area is called the index. If you don't see a number there, it is automatically a square root, but you can have a cube root where the index is 3, the fourth root, fifth root, etc. And finally, under the radical sign, that is called your radicand. Now, the most important thing is reducing radicals. Just like you reduce fractions into their lowest terms, you have to reduce radicals. And it involves you breaking down that radicand into the product or the multiplication of two numbers where one of them has to be a perfect square. So I have all the perfect squares from your 1 times 1 to 12 times 12 written out because those are the ones that you're typically going to have to use. So let's get started. With the square root of 75, I have to think about what two numbers multiply to give me 75, but one of them has to be a perfect square. And that multiplication would be 25 times 3. So I'm going to rewrite the square root of 75 as the square root of 25 and the square root of 3. Because if I were to multiply them, I would get the square root of 75. Now that I have a perfect square, I know what the square root of 25 is. It is the whole number 5. And the square root of 3, that can't be reduced. So this is your final reduced form. Let's try again. The square root of 48. Now you might say, 4 times 12. But 4 isn't the greatest perfect square that you can use. 48 can also be written as 16 times 3. And 16 is also a perfect square, and it's a larger one. So you always want to use the largest perfect square you can, or else you haven't fully reduced. So instead of writing the square root of 48, I'll write the square root of 16 times the square root of 3. And now the square root of 16 is just 4, and the root 3 is not changing. And this is always a step you have to take, whether it's at the very start or at the end, to make sure your radicals are reduced. And if we look at this final example for reducing, I have 3 different radicals, so I'm going to reduce all 3 of them. Now, the square root of 12, I can write that as the square root of 4 times the square root of 3. Now, for all of these examples, I like to put my perfect square in the first radical because I know that one will turn into the whole number, and I always like my coefficient out on the left side. And then 18 can be written as 9 times 2, so the square root of 9 times the square root of 2. And the 64, it's already a perfect square, so don't go breaking it down into 8 times 8 or 4 times something. 64 is already a perfect square, so I'm just going to reduce it right away to the nice whole number of 8. So always look out for that. Sometimes something is already a perfect square. Don't break it down, just turn it into its whole number. So now the square root of 4 is 2, so I'm left with 2 root 3 to represent root 12. The square root of 9 is 3. So I'm left with 3 root 2, and then the minus 8. And this is fully reduced. And here you can't start adding or subtracting anything, which leads us into the second part. In order for you to actually add and subtract radicals, they have to be like radicals. And like radicals just mean you have to have the same radicand or the same number under the root symbol. It's just like when you're adding or collecting like terms with x's and y's. You can only add x's together or x squares together. So here you can only add things like if they're both the square root of 5, then you can add them together. So let's try this first example. If I look over here, I have a square root of 5, and I have negative 3 square root of 5. And then I have 4 root 3 and 2 root 3. And for this first example, I'm just going to rearrange this, and then I'll collect and add. So I'll put my root 5s together, and then I'll put my root 3s together. And notice when I rewrite this, the symbol that was in front gets moved with that term. And now I have 1 root 5, and then I'm subtracting 3 root 5s from it. 1 minus 3 is negative 2. So I have negative 2 root 5s. And then for the root 3's, I have 4 plus 2, that's 6 root 3's. Notice the coefficients get added or subtracted, the radicand stays the same. Think of this as if you had 4x plus 2x, it becomes 6x. The x's do not change, same idea here. Now if we look at the next example, you will notice that you do not have any like radicals, but we should remember that we always have to reduce radicals if we can. And if we reduce these, some of them might become like radicals. So instead of the square root of 24, I'm going to break this down into root 4 times root 6. The 3 stays where it is, and instead of the square root of 50, I'll break it down into root 25 times root 2 plus 2. The square root of 54 can get broken down into the square root of 9 and the square root of 6. And finally, the square root of 32 can get broken down into the square root of 16 and the square root of 2. And 32 you might have also thought of 4 times 8, but that 8 would be broken down even more, so you know there's more that you can do. That's why you want to pick the highest perfect square. Now let's clean this up a little bit and then we'll collect our like radicals. So root 4 is 2, so we have 2 root 6. Now here, I already have a coefficient out in front. I'm going to go the long way. I'm going to keep the 3 where it is, and the square root of 25 will turn into 5. And the root 2 stays there. Now remember, all 3 of these parts, they're being multiplied. So we'll deal with that in the next step. Same thing here, the 2 stays, the square root of 9 becomes 3, and then we have root 6, and finally 5 times 4, and then root 2. Let's clean this up and then we'll collect. 3 times 5 is 15, so we have 15 root 2. 2 times 3 is 6, so 6 root 6. 5 times 4 is 20, so 20 root 2. Now, I find my like radicals. So the 2 root 6 gets paired up with the 6 root 6, and the 15 root 2 will get subtracted with the 20 root 2. And now we can clean up. 2 plus 6 is 8, so I have 8 root 6's. 15 subtract 20, negative 5, and then root 2. Remember, the sign in front belongs to the term. So don't do 15 plus 20. It is 15 subtract 20 because of that negative attached to the 20. And now this is as far as you can go. So for adding and subtracting, you need to find those like radicals, and sometimes you have to reduce beforehand. And just remember, with like radicals, when you add or subtract them, you add and subtract the coefficients. The radicands stay the exact same. Now, the next operation is multiplying radicals. When you multiply radicals, you will multiply the coefficients together, so the numbers in front of the radical signs, and then you'll multiply the radicands, so the numbers under the radical signs. So if I look at this first example, I have 2 root 6 times 4 root 3. I'm going to do 2 times 4, and that's 8. And then for my radicands, I'll do 6 times 3, so the square root of 18. Now your final step is always going to be, can I reduce this? And the square root of 18 can be broken down into the square root of 9 times the square root of 2. And the square root of 9 is 3. And then we'll multiply our 2 coefficients. 8 times 3 is 24. So 24 root 2 for this product. Now, in our next one, we have a distribution. So I need to take this root 2 and distribute it into the 2 terms that are inside my bracket. Now, I want you to remember that there is technically a coefficient of 1 in front of the root 2. So when I multiply, the coefficients will get multiplied by that 1, and the radicands will get multiplied with that root 2. So when I do root 2 times 2 root 5, 1 times 2 is 2, and 2 times 5 is 10, so the square root of 10. Minus 1 times 3 is 3, 2 times 8 is 16, so the square root of 16. Now, we have to reduce. The 10 cannot get broken down more, It can be written as 5 times 2, but that's useless because that's not a perfect square. And for this next one, don't break the 16 down into 4 and 4. 16 is already a perfect square, so we can just reduce that right away to the whole number 4. And our final cleanup, 3 times 4 is 12. So that's your final answer. And now to increase the level one more time, let's do a distribution with 2 binomials, which means we're going to apply that FOIL shortcut. So I'm going to multiply root 8 by 4 root 2 first. The coefficient is just 1, so I'm doing 1 times 4. And for the radical, 8 times 2 is 16. Then I'm going to do the square root of 8 times negative 2 root 5. So 1 times negative 2 is negative 2. 8 times 5 is 40. Now I'll take my second term. 3 root 5 times 4 root 2. 3 times 4 is 12. 5 times 2 is 10. And finally, 3 root 5 times negative 2 root 5. 3 times negative 2 is negative 6. And 5 times 5 is 25. And now we clean up. And I do notice already that these square root of 16 and the square root of 25, those are already perfect squares, so I can turn them into their nice whole numbers. So this will become 4 times 4. And the square root of 40 will become square root of 4 times square root of 10. The square root of 10 cannot get broken down more. And the square root of 25, I can write it as just 5. And now we clean up. 4 times 4 is 16. I can rewrite the square root of 4 as 2, so I'll clean that up in the next step. And 6 times 5 is 30. And now I will collect my 16 and my negative 30 at this step. And 16 minus 30 is negative 14. 2 times 2 is 4 root 10s. And they're both root 10s, my final radicals, so I can collect these. So I am doing not 4 plus 12. I'm doing the negative 4 plus the 12. So I end up with positive 8 root 10. And that negative 14 is still on the outside for the constants. And that's your distribution with binomials. A little more tedious, and you're using all of your knowledge of radicals here. You're using your multiplication knowledge, you're simplifying, and you're collecting and adding and subtracting. Now I want to do one more distribution example because this distribution is a little special. If you look at the two brackets, the terms are the exact same, except one bracket is addition and one bracket is subtraction. So it kind of looks like a difference of squares if we're thinking about the factoring connection here. So I am going to do a full distribution just to show you what happens in a shortcut in this particular scenario, because we will need it in our final step. So I'm going to do root 6 times root 6, and they're radicals, so 6 times 6 is 36. Root 6 times negative root 3 will be negative 6 times 3 is 18, so root 18. Then I take the positive root 3 and I multiply it by positive root 6 to get positive root 18. And positive root 3 times negative root 3 is negative square root of 9. Now you will notice that our middle terms are the exact same but opposite operations, and they cancel out. And that will always happen when your brackets are identical except for the positive negatives, because of that difference of squares. And you know with a difference of squares that the starting unfactored expression is a binomial. And now if I reduce this and clean it up, the square root of 36 is 6 and the square root of 9 is 3. And notice the 6 and the 3 are the radicands from the two terms in your brackets. And the reason that happens is because when you multiply a radical by itself, it's like taking the radical and squaring it. And a radical and an exponent, they're opposite operations. So I'm actually just going to make a little note here. When you did root 6 times root 6, it's the same as you doing root 6 squared. And those operations cancel each other out, and that's why you're just left with 6. So you actually don't even have to write the square root of 36. When you see a radical being multiplied by itself, the answer is just the radicand. And now 6 minus 3 is 3. Now we're going to take that and apply it in a little bit when we do something called rationalizing our denominator. Now to rationalize the denominator, it is something we have to do because we are not allowed to have a radical in the denominator. And there are two scenarios we're going to deal with. One is when we have just a single term in the denominator with a radical, or when we have two terms. So for the first part, when you just have a single term, I don't want the radical in the denominator. So in this first scenario, that root 5 is no good. So if I want to get rid of it from my denominator, from what we just saw, if you multiply a radical by itself, it becomes a nice whole number. So I want to multiply the denominator by root 5, and that will solve my problem. But I know whatever I do to the denominator, I have to do to the numerator as well. So I'm going to multiply the top by root 5 as well. So now when I do that, my numerator will become 3 root 5, and the denominator will become a nice whole number of 5. Yes, you can go the long way and write the square root of 25 and then bring it down to 5, but you don't need to because we know the connection of radicals and exponents of 2. Let's try the next one. For the next one, I have a radical in the numerator as well, which doesn't bother me at all. What bothers me is the radical in the denominator, and I don't want it there. To get rid of it, I need to multiply by root 3, and whatever I do to the bottom, I'll do to the top. So now my numerator, because they're both radicals, I'll do 6 times 3, so it's a square root of 18, over root 3 times root 3 is just a nice whole number of 3. Now, that square root of 18, we can actually break it down into the square root of 9 and the square root of 2. We have to reduce, and we can't forget about that step. When I reduce the square root of 9, that is 3. And now I notice that the coefficients here, 3 over 3, they become 1. So they cancel out, and my answer just becomes root 2, which is a lot nicer than that root 6 over root 3. So we always have to reduce. And that's if you have a single term where you want to multiply by the radical that is in the denominator. But you do that to both the top and the bottom. Now, for two terms, we have to apply that difference of squares knowledge. We noticed in the previous example, this bottom one, when I multiplied this bracket, the root 6 plus 3, by the same bracket but with the opposite sign, the radicals disappeared because the middle ones disappeared, and the outsides were perfect squares automatically, and it turned into a nice whole number. So we're going to apply that idea to two terms in the radical. And when you have the same bracket but one of them is the opposite sign, that is called a conjugate. So for this first example here, we're going to multiply top and bottom by root 6 minus root 2, the opposite sign of what is in the denominator. And I'm going to make a note that this is called the conjugate. Now, in the denominator, I'm not going to do an entire distribution because I know the middle terms will disappear because we just saw that. Instead, the denominator will just become 6 minus 2 because I know I would have the square root of 36, but that's just 6. The square root of 4 is just 2. And it's going to be subtraction because positive times negative is negative. And on top, I'm just going to keep the 3 times the square root of 6 minus the square root of 2. And I'm not distributing the 3 just yet in case things can simplify. So when I simplify my denominator, 6 minus 2, I get 4. And I know that original coefficient of 3 in the numerator, that's not going to cancel out at all. So I will just distribute the 3 in at this point. So that is it. Yes, I have radicals in the numerator. That's not a problem. I have gotten rid of the radicals in the denominator because that was my issue. Now let's go to the next one. So for the next one, we have 2 root 2 minus root 5 in the denominator. That's no good, so I'm going to multiply by the conjugate. And the conjugate will be the exact same thing, but instead of subtraction, it will be addition. And whatever I do to the bottom, I do to the top. Now, my original numerator is also a binomial, which means when I do my distribution for my numerator, it is going to become a full distribution with FOIL. Now, I am going to clean up my numerator first. So I will do the full on FOIL. 2 times 2 root 2 becomes 4 root 2. I multiplied the coefficients and the radical stayed. 2 times root 5 is positive 2 root 5. Root 3 times 2 root 2, the coefficient stays. But root 3 times root 2 is root 6. And finally, root 3 times root 5 is the square root of 15. And nothing in that numerator is going to reduce or collect. Now for my denominator, I know all that's going to get multiplied are the 2 first terms and the 2 last terms. So 2 times 2 is 4, and then the root 2 times root 2 will be 2. Minus root 5 times root 5 will just be 5. So I will have to clean up that denominator. I'm going to rewrite the numerator because nothing can reduce, nothing can collect. 4 times 2 is 8, and 8 minus 5 is 3 for that denominator. So this is a lot more tedious, especially when you have another binomial in your numerator as well, because you have to do a full binomial distribution. And now let's try the last one. If you would like to pause the video and try it out on your own, that would be a great idea. Otherwise, I am going to take it up right now. So what I will be multiplying my numerator and denominator by is the conjugate, which would be 3 root 2 subtract root 8. And I will do that to the top and the bottom. Now, for the numerator, because it's just a single term on my original fraction, I'm not going to distribute it just yet. So I am just going to write the negative 4 as is. And in my denominator, I'll multiply the 3 root 2 by itself. So 3 times 3 is 9, and root 2 times root 2 is 2, minus root 8 times root 8 is 8. And now I'm going to clean it up. For my numerator, I am going to reduce that root 8 because I know I can write it as root 4 root 2. And in my denominator, 9 times 2 is 18, and 18 minus 8 is 10. And now, just looking at these coefficients, I can reduce them into, instead of negative 4 over 10, negative 2 over 5. And I'll rewrite my bracket. So 3 root 2 minus 2 root 2. And now I actually have like radicals in that bracket. So I'm going to collect them and then finish this off. So 3 root 2 minus 2 root 2 is 1 root 2. So I actually don't even need the bracket. All over 5. And this would be your final answer. No radicals in the denominator, so that's great. We've reduced everything. Everything has been collected, and that's it.